Hello, my name is Ajay Joshi. I work as a technologist in Western Digital. In today's presentation, I will talk about how to leverage computational storage in data analytics using PostgreSQL. So the agenda would be that we would look into the cloud infrastructure, a little bit of data analytics, and then what is computational storage, the model which we have built, results, and key takeaways. Cloud infrastructure is basically disaggregated. Resources are decoupled, so the storage, compute, and memory can all sit at different locations. All these are connected via high-speed network. Storage is also often remote, where the connection is basically based on NVMe OF interface. So the fabric of choice is basically the TCP when you go for NVMe OF. So all this is good, but it increases the distance between the compute and the data. Network is fast, but the problem is as we keep the compute far away from the actual storage data, the latencies will be very high, and hence it will also increase the it will also lower the throughput. Because the network is basically 100 gig or 50 gig network, we may hog up the network when we are doing large amount of data transfers from the same SSD. So on top of that, the storage throughput is growing at a much higher rate compared to CPU and DRAM throughput. So when we have the compute access the SSD, which is sitting across a network, which is a 100 gig network, so they can have multiple access to the same compute can access multiple SSD, leading to network congestion. So considering all this, what can we do? So the simplest answer would be to move compute closer to the data. So in the previous slide, we noticed that an increase in the data transfer would lead to a lower latencies and hence lead to the network congestion. So the best thing would be to move the compute closer to the data. So when we move compute closer to the data, we can do a much lesser transfer based on our requirements, based on what we are trying to transfer. We can just only transfer the selected part rather than doing a transfer for the whole data itself as such. Where does this generally go? Where does the need for the compute to move closer to the data come in? It's most of the time in data analytics kind of an requirement where all this would be needed. What is data analytics? Data analytics is actually a process of analyzing raw data. So what we're looking at in data analytics would be a specific patterns in database. For example, looking for a date of birth or a ship date would be one of those use cases. So how do we leverage all this data using a database? In the database is using SQL statements. So SQL is basically structured query language. So it is simple English like statements where we actually filter or get the data and work on the data, leverage the data, and as well as read and write to the data in terms of need. So all this can be written using a query. The query is basically can be split into three different parts: scans, filters, and the compute part itself. For example, in a simple query, so we have a table T1 where we're trying to look a data value between greater than 10 and less than 2 million. And then after that, we're trying to count how many of them are there. So basically the three parts would be that you can scanning from the table T1, filtering the data based on the filter requirements, and computing all this data. So what we notice is that when you have a huge amount of database, the data transferred across the network is 20 gig or 100 gig based on the database size. Whereas in this particular case, the data of interest is just 72 MB. So as you keep increasing the database size, the amount of data transfer keeps going more and more. So what can we do? So the easiest answer would be to move the scan and the filter operations closer to the data so that we can just transfer only the data of interest, that is 72 MB. So how do we do it? One of the easiest mechanisms is using PostgreSQL. So PostgreSQL is one of the most widely known object relational databases. So it has lots of query scanning options where it can do multiple scans for the queries. So one of the supported scan is called a custom scan. So it has APIs for custom scan where we can interface our own scan mechanism there using GPUs or FPGAs, and then and when the query comes in, we figure out if that query is actually to us or not, and then relevantly access our scan mechanism. The best part about PostgreSQL is the data itself as such, how it is stored. The data table itself is stored in pages. The data in the table is stored is in terms of pages of 8K to 16K kind of pages. So each of these pages is basically has a well-defined format. So where, for example, it has, in case of ordinary table format, you have a page header, item, and the tuples all located as a part of the 8K page itself as such. The tables are generally in gigabyte segments. So if you have a 20 gigabyte table, and it's all split into 20 each 1 gig files. So the scans can be done in parallel for that. So with considering this, since all this is well defined, the structure and the table and the table format are all well defined. So can we move the scans here to the hardware was the question we had. So we started looking at computational storage from that perspective. So according to the SNIA definition, the computational storage is defined as architecture that provide computational storage functions coupled to storage, offloading, host processing, or reducing data movement. In other words, the computational storage brings compute closer to the storage. So it becomes, we can process the data directly on the storage rather than having to bring it across the network or across the CPU transfer medium to process on this data. So the advantage of having the computational storage is to reduce the storage to CPU bottleneck. So with all this in place, how can we do the offloads here as a part of the storage itself as such? The offloads defined by SNIA are of two types: fixed computational storage services and programmable computational storage services. In our model, we looked at the programmable computational storage model, trying to leverage that for our custom PostgreSQL scan. So we had our model consists of two major components. One is the host and the offload target. The host itself is basically where the PostgreSQL runs, and we created our own plugin called WDCS plugin. It interfaces the entire PostgreSQL with the offload target. It passes the queries which comes into the PostgreSQL, and it looks at all the SQL statements and sees that whether any of the statement makes sense for us to offload a target or not. Based on that, it takes a call to whether enable the offload scan or not. So once we have this in place, it also defines that how would be the tuple format. That is the page what we saw in the previous slide has a defined tuple. So these tuples, how are they organized? What is the data content of it? What are the data contained in those tuples? So, and what is the format of this data is all understood with the WDCS plugin. It also understands from the SQL statements that what are we filtering at. So based on this, it prepares a list of descriptors, which it prepares, which it would pass on to the offload target for the scan mechanism. So next, it also prepares the offload code. So actual code, what has to be offloaded onto the executor, so that it can scan the data and give the filtered result. So it also prepares that offload code. It also programs this code to the target and initiates the scan. The offload device itself, or the offload target itself, is basically an NVMe based device, so which is connected over an Ethernet. So it has a computation storage controller. It handles the various commands coming out of the WDCS plugin, so that is connected to the PostgreSQL. It manages the resources connected inside the target, and it also manages device various states. It has executor module, which actually runs the offload code. So what the WDCS passes in, so that offload code would be run as a part of the executor module. It also has DRAM, where all the data from the SSD, the results, and the descriptor data itself are stored. It also has a mechanism to read the data from the SSD without the CPU intervention to the DRAM directly. how do we fit in all this together? Like, for example, in the host and the target case, so there are four different modes of operations what we do. The first mode of operation is where where the WDCS controller extension, WDCS extension writes the offload code, tuple format, and the filter descriptor to a RAM region. So once we have that in the RAM region, it asks the next WDCS plugin would ask the CS controller to load a set of LBAs from the SSD to the RAM region 2. So once it has that in place, the offload, it triggers the offload code to access, it triggers the offload code to start executing. The offload code will pick up the tuple, the filter descriptor, it will pick up the LBA data, and then it will pass in its code that how the LBA data is organized and what are the tuple format and what are the filter we are looking for. Based on that, it will filter the data available and put it into a RAM region 3 called as a results region. So once the execution of the offload code is completed, it triggers to the CS controller that it has finished the execution of the code. So once the WDCS plugin gets the information that the whole operation is completed, fetches the results from the results region and passes on to the query which asks for this particular filter result. So we did a analysis of how much of the two setups, the one setup without the offload and one setup with the offload. So in the without the offload, we had an NVMe OF drive connected directly to PostgreSQL. And in the offload case, we had a target, which was NVMe OF target, but were capable of doing the offload processing as such. So with all this, we ran two kinds of query. The simple query is what I had mentioned in the previous slide, and a TPCH query. TPCH is basically a decision support benchmark from TPCH, from tpc.org. It is used to analyze different databases and how the responses to various queries. They are defined, the definition of the TPCH also contains what is the data format, how is it stored, and each query, what has to be executed. So we ran a simple query and as well as a TPCH query. In both the cases, we noticed that the total data transferred is much lesser compared to the without the offload case. And without the offload case, we had to transfer the execution time itself. So the execution time itself was about 110 seconds compared to just the 20 seconds, which was there in case of a simple query. The same happens with regards to the data transfer itself as such. The data transfer itself was about the same as the database size, whereas the data transfer in case of an offload case was about the data of interest. In this case, the simple query case, it was 72 MB, whereas in a TPCH query, it was about 150 MB of data transfer. So with this, if you have a sufficiently bigger target or a sufficiently larger CPUs, then the execution time can be further reduced. Based on the target and the configurations, we can have different. You can have a better solution and a better architecture of how all these things work. So with all this, we were trying to understand whether, in conclusion, we wanted to understand that what are the key takeaways from our model. The major takeaway is that offload is awesome for workloads which involve sequential scans. So the best it would be one of the best approaches if you are doing a sequential scan, because the data is well organized and it is in the form of LBAs are one next to each other. It becomes much easier to scan and process that. It is easily scalable, so you can have multiple computational storage devices and then have that scan split across multiple devices. So you can have a device having multiple CPUs where you can do a part of the scan in each of the CPUs and then consolidate the result in kind of a leader node kind of a thing and then give the result. So there you can easily scan to multiple devices and have the same sequential workload doing much faster. It would reduce it will also reduce the host CPU, memory, and the network loads. The memory usage would definitely come down. The CPU would be free to do much more amount of work than what it was doing when it was processing the network. And definitely the network load will reduce because we are not transferring the whole data now, only the selected data we are transferring. All this makes sense for what for the workloads what we define, but there are some drawbacks we see there with regards to this model itself as such. So when you look at the index scan or scattered scan, they may end up worse compared to what you do in host. We may end up in a very bad result when we do it in the offload case itself as such. Subsequent scans may be much faster in a host compared to the offload device, because there is no caching mechanism in an offload device. We can have caching mechanism in host-based scans, but it may not be possible here. Updates to the system itself, when you are actually have a bug or basically adding additional features, so then basically it may involve the system downtime, whereas in a host you can just restart the entire thing, because it's just a software drone. We may do the whole thing and we have to just restart the entire process as such to make it work again. But in here it may involve actual system downtime. In some cases where we find that the queries can be rewritten to give a better performance than doing an offload, that is one of the things which we also noticed. We also can change the way databases store the data itself, can have a different schema, and then hence optimized its IO loads. So we can do that as well. So in conclusions, all these are our key takeaways from this. That's about it from our presentation. Thank you. Thank you for attending this session.